Good morning, Algebra 1 CP students. Hopefully you're having a fantastic day so far. I am coming at you from home today, but that does not stop us from getting some math done. All right. My layout might look a little blank on the screen. That's because it was filled with last year's information. That's a little bit outdated now, but you can still see me. You can still see what we're doing, so we're going to roll with this. Today, what I'd like to show you is I'd like to show you how to solve linear equation word problems. By that, I mean there are scenarios that in order to solve them, we need to create equations very similar to the ones that we've created in class. Quite frankly, the equations we're going to make now are much easier to solve than the ones we did in class, but the challenge is translating those words to equations. That's the big challenge. With not just these types of word problems, with any word problem, the challenge I think and where students really struggle and why this negative perception of word problems exists is because it's difficult to translate words to math. But once you're at the math, then it's just solving equations like we've been doing all along. Okay, so I'm really going to focus on the translation today from words to math with these types of word problems. And then tomorrow I'll delve into some more of the traditional linear equation word problems that you may see in on like an SAT or some sort of similar exam. All right. So to get started, and I know my layout is a little bare here because I had a lot of information from last year on it, so it's a little irrelevant now. So whatever, you can still see me, you can still see what we're doing. To get started, I want to just show you this cool little worksheet that I found, and I will post this on Google Classroom for you. I think this is super valuable and pretty much tells you just about everything you need to know. When we're going through these types of problems, what you really want to do is look for key words and key phrases, okay? When you see over here some stuff like plus, more than, the sum of, the total of, increase by, added to, all of those words, all those keywords and more, that there could be others, but all of these keywords indicate that we're probably going to be adding things together, right? Like 3 more than something, for example, would mean we're going to do 3 plus something, okay? Subtraction really corresponds with these words: minus, less than, the difference of. Remember, difference is the answer to a subtraction problem. Less, decrease by, subtracted from. Multiplication goes with times, the product of, twice or double or triple or any of those types of words. Multiplied by, and then of, like 3/4 of a number, means that we're going to multiply by 3/4. Okay? Division goes along with the quotient of, divided by, the ratio of. You could also hear this as half or 1/3 or 1/4, means we're going to divide by 2, 3, and 4 respectively. Powers we're not really going to see quite yet, but still important if you want to note that the square of and the cube of or cubed means we're going to square them and cube them. Again, not really coming up yet because we're only dealing with linear equation word problems, but later on in the year we'll definitely see those. And then equals. I think equals is probably the most obvious, but like when you see the word equals or is the same as, is equivalent to, amounts to, yields, all those types of words mean that that's when we're going to put our equal sign. Okay, so I think this is a super valuable resource. Again, like I said, I will post it on Google Classroom for you so you can have that to look at. But that being said, our general strategy with solving these types of problems, so I'm going to say right here, our general strategy really comes in 3 steps. The first step is I'm going to translate the scenario to an equation. And like I said, I think this one is the one that students struggle with the most, and that's why word problems sort of have their unfortunate negative reputation, even though they are really great applications of things that you've learned. But the first one is to translate scenario to the equation. Okay. Second one is once I have my equation, I want to now solve the equation or solve the resulting equation. For us, I think at this point, solving the resulting equation is going to be the easy part because we've been working with solving equations. So solving equations at this point should feel pretty comfortable. Okay, and like I said, the equations we get here will probably be even easier than the equations we've seen before. And our third step is we want to answer the question being asked. I know that seems obvious, But a lot of times in a word problem, especially when we come up with an answer for x, when I get to the point of like x equals some number, a lot of students stop and a lot of students put a box around it or a cloud or a highlight or whatever you guys do. But that sometimes isn't actually answering the question. So it's important that we take the information of what x is equal to and go back to try and solve the actual problem being asked. Okay, so those are our 3 real steps. Let's take a look at these examples here. Again, I'll try to highlight some keywords and where I'm translating certain things. I have 3 on the front, I have 3 on the back, and then we'll be good to go for the day. All right, so starting here, it says, Billy is 5 years older than his sister Sally. If the sum of their ages is 39, how old is Billy? So I see a couple keywords right away. I see sum means that we're definitely going to be adding Billy's age and Sally's age together to find this total of 39. I also see that Billy is 5 years older than his sister Sally. So what that means is if Billy's 5 years older than his sister Sally, I would ask, how old is Sally? Well, we don't know, right? So I would say that Sally's age can be represented by X, right? We don't know how old she is. You can use whatever letter you want, but X is usually the go-to. So I don't know how old Sally is, so I'm going to say X, but I do know that Billy is 5 years older. So 5 years older means 5 more years, so we're going to write Billy's age as X plus 5. Do you see that? Because 5 years older would mean take Sally's age and add 5. It then says the sum of their ages is 39, so sum means we're going to add things together. We're going to take Sally's age plus Billy's age and say that that is 39, right, equals 39. So I'm going to set up my equation to be X, Sally's age, plus X plus 5, that's Billy's age, equals 39. Hopefully that made sense how we set that up. And now, if you notice, like I said, this so that's the hard part, in my opinion. The hard part is translating the words to the math. But now, this is very straightforward. If we want to solve something like this, we're just going to combine like terms. On the left side, we have 1x plus 1x is 2x, plus 5 is equal to 39, right? I can then subtract 5 from both sides. To isolate the x gives me 2x is equal to 39 minus 5 is 34. And lastly, divide both sides by 2, and you get x is equal to 17. Okay? Once again, though, I don't want to stop at this particular point. Again, I think that this problem-solving process is fairly straightforward. I don't want to stop here, though. It's a very common, again, misconception, and it's very tempting to just say, oh, x is 17. Done. Let's move on to the next one. But what is the question asking? The question is asking, how old is Billy? Well, right here it says that Billy's age is x plus 5. So if x is 17, then Billy's age is going to be x plus 5, or 17 plus 5, right? So Billy is 22 years old. And now that's the answer that you can put a box or a cloud or a highlight around. Okay? Any questions about that? Hopefully we're pretty straightforward. Oh, that's pretty straightforward. Let's do a couple others. I remember always struggling with these when I was younger. But it's now that I kind of understand how to translate them, I think it's important that, I don't think they're that bad anymore. I think it's important that you try to do the same sort of process. It says, second problem, John worked 5 less than twice as many hours as Jane did. So that statement, I remember being like very confused at statements like that. I'm like, first of all, who talks like that? Nobody says, oh, I worked for 5 less than twice as many hours as Jane. But that may be true, but it is a good exercise in trying to build these types of equations, okay? So we have John and Jane working. I'll get to the rest of the problem in a minute. So we got John and Jane, okay? John worked 5 less than twice as many hours as Jane. Well, how many hours did Jane work for? The problem doesn't say, so I'm going to represent Jane with an X, okay? Now, John worked 5 less than twice as many hours as Jane. So take Jane's number of hours worked, which we just signified as X, double it, because it's going to be twice as many, and then subtract 5, because it would be 5 less than that, right? So twice as many hours as Jane did means I'm going to take Jane's number of hours and double it, And then I'm going to say, oh, well, John worked 5 less than that, so I subtract 5. Okay? Sometimes it can be beneficial. I always find a cool strategy is instead of reading this way to sort of, read the sentence in general English, I almost build my equation by reading to the left. And I say, well, we're going to do twice as many hours first, and then we're going to take away 5 from that. Okay? So 5 less than twice as many hours. Now we go to the second part of the equation and say, well, how many hours did each work if together they worked 97 hours? Well, together means we're going to add them, right? They're going to combine them. So I'm going to say they each worked together 97 hours. So John worked 2x minus 5 hours. Jane worked x hours. And together they made that total of 97. All right? Hopefully you understand that step, because then going forward is the easy part. So now you're like, oh, I just did the hard part. I did the word problem essentially. Now I can just do the straight algebra. 2x plus x is 3x minus 5. Notice I combined like terms on the left side. Equals 97. I can add 5 to both sides. I can get that 3x is equal to 97 plus 5 of 102. And I can now divide both sides by 3, and I believe we'll get x equals 34. Okay. Does everybody see that, hopefully? Now, if x equals 34, again, that does not answer the question. It's very tempting to put a box around that and call it a day, but we can't call it a day yet. The question is, how many hours did each work if together they worked for 97 hours? So how many did they each work? If x is 34, then that means that Jane worked for 34 hours. But what about John? Well, John would have worked for 34 times 2 hours minus 65. So we would have to take our 34 and substitute it in for the x, or plug it in for the x, right? Just to give myself a little bit of room, I'll do it down here. We would say that John worked for 2 times 34 hours minus 5. Way more than Jane, right? 2 times 34 is 68. 68 minus 5 is 63 hours. So your actual answer to the problem is not just x equals 34. You would say Jane worked for 34 hours and John worked for 63 hours. And notice that you can always go back and verify the fact that, yes, 34 plus your 63 does total 97. All right, let's keep going. Next problem is, again, kind of a no-frills problem here. We're not introducing any names. We're just saying 3 times the difference between a number and 10 yields 15. Find the number. So the difference between a number and 10, right? 3 times the difference between a number and 10. So the difference, as that worksheet that I displayed to you suggested, and as you may already know, difference indicates subtraction. So when I have the difference between a number, I'll call this number x, right? A number, and 10, that means I'm going to do the difference between a number and 10 is x minus 10. Right? Because the difference is subtraction. So the difference between a number and 10 is x minus 10. Just like that. Okay? Now, if I want to do 3 times that difference, I'm going to say, well, here's the difference of a number between a number and 10. And now 3 times that difference, so multiply by 3, is going to equal 15. Yields 15. Right? So notice how we translate those keywords just one step at a time. The difference between a number and 10, x minus 10. I take that difference and multiply it by 3 or triple it. Put that there. And then we yield 15. Now I can solve this problem with a little bit of distribution. I'll take this 3, multiply it here, and multiply it here. I get 3x minus 30 equals 15 after we apply the distributive property. This is now our familiar 2-step equation that I know and love. So we can add 30 to both sides. That gives us 3x is equal to 45. Next, divide both sides by 3 to get x alone. And I get x equals 15. Hopefully I'm not going too fast when I solve problems like that. But I think our solving equations should be pretty comfortable at this point. Okay? And if you notice, I did just put a box around x equals 15 because that actually was the question. In this particular case, we didn't have to do anything with that information. It just was asking us what number makes this all work out? 15. Alrighty. Okay, let's transition to the backside because we've got some new vocabulary to throw at you here. So on the backside, we see this problem up at the top. It says the sum of 3 consecutive integers is 174. Find the 3 numbers. So just to make sure we're comfortable with this vocabulary, consecutive. All right. Consecutive, I'll define it for you here. It's a big fancy word for in a row, all right, or adjacent, okay? Consecutive integers come all in a row, one after the other, okay? So like, for example, 3 consecutive integers could be 5, 6, and 7. Those are 3 numbers that come right after each other. Obviously, not going to be the answer to this problem, but those are 3 consecutive integers, okay? So there are 3 things that come in a row. How do we translate that, though, to an equation? Well, clearly, we're doing the sum, so we can add them all together, right? Let's think, though, of how to construct these 3 numbers. The first number, we don't really know where we're going to start, right? There's really no indication of what number we would start at, so I'm going to call my first number x. Right? Now, if my second number is going to be consecutive to the first, meaning it's going to come right after it, I'm going to say, oh, well, if my first number was x, my second number will come right after that first one. Or in other words, I can represent that with x plus 1, right? Think if x were 6, then the second number would be 7, the number right after it. And my third number, now, if we were starting at x, we would add 1 to get here and add 1 to get here. We can represent this as x plus 2, right? Because it's 2 now away from my first number. So now that I have a way to represent all of those consecutive numbers, I can find their sum, set it equal to 174, and go from there. I can say, well, my first number x plus my second number, x plus 1, plus my third number, x plus 2, equals my 174, and I'm trying to find the 3 numbers. So let's try to solve for x, and then we can go back and say what our 3 numbers were. Let's combine like terms first. On the left side, x plus x is 3x, right? I have 1x, 1x, and 1x. I have 1 plus 2, which I'm going to combine to make 3, right? Notice the like terms combine, and these like terms combine as well, equals 174. This is now a familiar 2-step equation that I love solving, familiar 2-step equations, because this is our happy place. This is when I can say, ooh, I know what to do here. I'm going to subtract 3 on both sides. That gives me 3x is equal to 171. Just rewrite it up here to give myself a little bit more room. I can now take both sides and divide by 3 because I want to get x by itself. I want to undo that multiplication of 3 times x. Fortunately, I do need a calculator for this one. 171 divided by 3. We get 57. So I get that x is equal to 57. Okay. Now, do we put a box around that and signify that as the end? No. The problem was asking, find the 3 numbers. So if I know that x is 57, that means my first number was 57, which means that my second number is going to be 58, and my third number is going to be 59. All right, so make sure that your answer here should be the 3 numbers are 57, 58, and 59. Okey-doke. And like I said, you could always double check your work and do 57 plus 58 plus 59, and bingo, 174, exactly what we were looking for. Okay. Hopefully no questions on that. Let's go to the next problem now. Not just talking about consecutive integers anymore, now talking about consecutive even integers. Interesting. 4 of them. 4 consecutive even integers. All right. Same idea where we're going to take these numbers, add them together, and try to get 100, right? You could probably see that here when we're saying they are 100. The sum is 100. 4 consecutive even integers. Well, I have 4 numbers here. My second, my third, and my fourth. Think of how we can translate, though, even integers, all right? If my first starting number is x, I don't know what my first starting number is, so there's really nothing better to call it than just x. My second number would be the next even integer that comes after that first one, right? So suppose my first one is 8, for example. The next even integer is 10, because the one right after would be 9 is odd, and then it's even. So every other number is even, correct? So instead of representing my second number as x plus 1, because that would be the odd number that comes right after, I want to skip over that odd spot to jump to an even spot, right? So I want to say that my next number is not x plus 1 here, but x plus 2, because that's how I would jump to the next even position, correct? Think of on a number line if you really want to, right? If I'm at 8 and I want to get to my next number, well, I don't want to include that spot. That's not a consecutive even integer because I want to jump from there to the next even integer, which is 2 away. And then I should have given myself more room here. From then, I want to jump from there to the next even integer, which is 2 more away, correct? So I would represent my third number as x plus 4 because I'm going to jump 2 to get here and 2 to get here, a total of 4. And then my fourth integer is going to be x plus 6 because we're going to make a jump of 2 to skip over the odd number to get here, another jump of 2 to skip over the odd number to get here, and another jump of 2 to advance 3 even integers away. Okay? Notice that if this said the sum of 4 consecutive odd integers, we would still be adding 2 because odd or even still skips over a spot. Right? So don't get confused now on another problem. You might be like, oh, it says odd. I don't know what to do. It's the same thing. We would just still skip over a position. Now we can take all these numbers. Now that we established that, we can take all these numbers, add them together, and get my sum, x plus 2 plus x plus 4 plus x plus 6 equals 100. Notice that's my first plus the second plus the third plus the fourth. All right. Also, notice what my question is asking for. It says find the largest number of the 4. So when I find what x actually equals, I want to make sure I identify what this value is. Now, let's go ahead and combine my terms. I have 1x, another x, another x, and another x, a total of 4 of them. I also have 2 plus 4 plus 6 all on the same side of the equal sign. So that's plus 12 equals 100. I've now arrived at a familiar looking two-step equation that I should feel very comfortable solving. I'm going to subtract 12 from both sides. Gives me 4x is equal to 88. And if I divide both sides by 4, we get that x is 22. Okay? But again, the question is not asking for what x is equal to. We want to take this value for x, which is 22, plug it into our fourth number because I want to find the largest number of the 4, and we would therefore realize that this fourth number would be 22 plus 6, or 28. Okay? And your 4 numbers, by the way, would be 22, 24, 26, 28. You can go ahead and check those just in case you're a little concerned and see, well, 22 plus 24 plus 26 plus 28 is 100, and they are, in fact, 4 consecutive even integers. Alrighty. Last but not least, one problem just to sort of wrap it all up together. We're going to go back to names and little scenarios here. It says, Katerina spent half of her weekly allowance playing mini golf. Love me some good mini golf. Very competitive. To earn more money, her parents paid her $4 to complete some chores. What was her weekly allowance if she ended with $12? So this good keyword here, ended with $12, means that we're going to be equal to $12 at the very end. Okay? Well, suppose that her weekly allowance started out as X dollars. I don't know how much her weekly allowance was. That's what I'm trying to find. So let's start that out as X, right? I'm going to say, well, she spent half of that playing mini golf. So she took her weekly allowance and spent half of it, means she now has only half of it left, or divided by 2, right? I cut it in half. That's how much I have left. If I had $20 and I spent half of it, now I have $10. 20 divided by 2, right? So that half is division. You could also multiply by 1/2 if you so desire. It's the same thing as dividing by 2. Now, to earn more money, so I was at this point where I spent half my money playing mini golf, and you're like, bummer. I need a little bit more. Well, her parents paid her $4 to complete some chores, so that's nice of them. I'm going to say, well, let's take our half now and add 4, because now we've gained 4 additional dollars, or Katerina gained 4 additional dollars. And now I ended with $12, so we're trying to find out what I started with, equals 12. Because after Katerina spent half on mini golf and then gained an additional 4, she's now left with 12. Does that make sense? Sorry, I kept saying because I love mini golf. I could just picture myself playing a nice game of putt-putt. I would spend half my weekly allowance on some mini golf personally, but anyway. So now I would go forward from here. This is a 2-step equation, and I can go ahead and solve, right? Notice again, some keywords that we're pulling out is spent half of her weekly allowance, paid 4 additional dollars, and ended with 12 equals 12. I can solve this by subtracting 4 from both sides. I get x divided by 2 is equal to 12 minus 4 is 8. Now, in order to get rid of that division by 2, I'm going to multiply by 2 on both sides, because that's the inverse operation. I get x is equal to 8 times 2 is 16. So that would mean that her starting weekly allowance was $16. So Katerina's starting weekly allowance is 16. Okay? Which, hey, if she had to pay half of that, $8 for a game of mini golf, I'd say that's well worth it. Well worth it. All right? Alrighty. Just a quick little recap, and then I'll call it a day. So what we did here is I went into how to solve some linear equation word problems. I went pretty in depth on trying to extract the translate the words to the math, right? Extract the equation from the scenario, because I think that's really the crux of all of this, or the key part of all of this, is being able to take these words and translate them to math. Once you have the equation, well, that's what we've been working on, solving equations like this. This should not be like a big point of stress, I wouldn't think, at this juncture, right? At this point, it should be pretty obvious to combine like terms and try to get x alone, right? Because those are the types of problems we were working on for a couple weeks now, all right? But the key is translating words to math. I will post a couple practice problems on Google Classroom for you. I would recommend trying to do them. I'll also post that worksheet that I showed just right at the beginning on Google Classroom as well, so you have it. But other than that, that's really all I have for today. Thank you so much for listening and for your attention and focus. I hope you have a great rest of your day, and thank you, everyone. I'll see you soon.